This piece of rubber represents a bar element, and we're going to say that the bar element is angled counterclockwise an angle theta from the horizontal. I'm going to define, well, it's a one, this is inherently a one-dimensional element, and I'm going to define a local coordinate axis. We'll call it X, and the X-axis runs in this direction. There's two nodes in a bar element, and the first node we'll say is at this location here. So we'll call that node 1, and then over here is node 2 at the other end of it. The bar element, all it can do is stretch or contract. It can't, a bar element itself, it can't rotate like this. That what we would call a beam element. So we're going to keep this fairly simple. Node 1 is by my left finger, and node 2 is by my finger on the right. The point I want to make with this video is simply the displacement function. So if I take node 2 and I displace it in the positive x direction, node 2 will be displaced a certain distance. Take a look at node 1 though. Node 1, my left finger, does not displace at all. Another thing I want to do is just draw a couple of more dots on my bar element along the length of it. So we've got a dot at that location, another one at that location, let's draw another one here. The only thing I want you to pay attention to is the displacement of each of these dots, and think about how the displacement is a function of the distance from my left finger, so the distance from node 1. As I displace it, the dot closer to my right fingers is displaced more, and the dot closer to my left finger isn't displaced as much. In fact, I don't know if I can do this very accurately, but here's the original location for that position on the bar element. And I'm going to displace my fingers about that much. And we'll just look the displacement after I've stretched it. If I can simply draw it here, maybe it would be displaced at that location. So if I try to reposition my bar element, take a look at this. That's kind of the displacement at that location of the bar. Let's contrast that with maybe I can capture the displacement at this location on the bar element. So there's the undeformed position of it. And then if I, oh, look at that. Yeah, if I displace it, the bar element again by the same amount, take a look at where that dot was displaced. If I draw approximate location of that displacement at that original location on my bar element, this is what represents the displacement function. So take a look at that as I move down further along the bar element. This dot here is displaced further. I didn't get that mark position correctly because I didn't have it in place, but you get the gist of it. The dot here is displaced more than the dot at that location. In fact, my left finger, the displacement is actually 0. So the displacement for a bar element will be linearly related to the position along that element. So in other words, it's proportional. It goes, the displacement function is 0 here, and it's the maximum value out here, and then intermediate values along the length of the bar. And we're going to say that, well, we're going to assume that this is a linear function. In reality, it actually is, but that is an assumption. We're going into this. Another thing to think about is, well, maybe node 1, instead of node 2 being displaced in the positive x direction, maybe node 1 is displaced in the negative direction. So the thing to think about is how the displacement of the element changes as I displace node 1 in the negative direction. So the thing to pay attention to here is that if I make that displacement, this dot doesn't displace as much. And in regions down here, the displacement is larger. So this, in essence, is a bar element. With my example here, the piece of rubber, what I can't do with this example, of course, is to hold node 2 fixed and displace node 1 in the positive direction, simply because the rubber buckles. But if you imagine mathematically, of course, this would just be compression. The nodes here would move more than the nodes here, and those nodes would be displaced in the positive direction. I just can't do it with the rubber. Another thing that I might do, maybe I'll displace node 2 to the right and node 1 to the left. So I'm simply stretching it. In that case, the displacement function for this type of deformation indicates that that dot in the middle is not being displaced. The dots over here are being displaced in the positive x, and the dots here are being displaced in the negative x direction. So these are all examples of displacements of a bar element. Note that this is a local coordinate system. Bar elements in general can be oriented any way that we want on the two-dimensional surface. And in that case, we do have to eventually convert the local coordinate axis into something that's global. And something that is a global coordinate axis will have components x horizontal and y vertical, but we just stick with the local for right now.